again, let us recap what we have learned so far. We have learned the characteristics of transducers, and then we learned the resistive type transducers. In that, of course, we saw the resistive potentiometer as a linear or angular displacement type of transducers. We also looked at floating wiper. Then we learnt about strain gauges, right, and its applications. Third, we learned about RTD, resistive temperature device. Fourth, we learned about thermistors, right? Thermistors, the characteristics is exponential, so we can linearize it using inverse exponential. If there is time, I will revisit this and talk about inverse exponential compensation for getting a linear characteristics output from the thermistors. Then we learnt about piezo resistive transducers. This again, piezo resistive, we will revisit a little later. When we talk about different types of transducers and what is happening today, there is also another type of transducer called magneto-resistive. So there are two type of magneto, tunneling magneto-resistive called TMR, tunneling magneto, and giant magneto-resistive transducers. These are quite popular nowadays. In fact, this technology actually helped the present day hard disks to store 1 terabyte. If you really look at the size of the hard disk and the capacity, that is mainly because of these two sensors, TMR and GMR sensors. I will talk about them, not here, because we are not really going to look at TMR and GMR in standalone transducer. We will look at their applications, specific applications for transduction principle, and of course the yesterday's very popular transducer called light dependent resistor, or simply LDR. And we also looked at the different signal conditioning circuits that go along with the resistive transducers. And today we start with inductive transducers. So first of all, what is an inductance? If I wind a coil, right, and I send a current I, the if there are n turns in this coil, then I create a magnetomotive force which is Ni. So we normally call this as ampere turns, AT, or today of course we don't use AT, we simply call A. This coil generates a magnetic flux, right? It generates a magnetic flux. Let's assume north and south. That's how we get the electromagnet, right? And so that's a flux line. And if the length, I call this as LM, then the uh, magnetic field created by this flux is called Ni by Lm. So the unit is ampere per meter, right? So if I have H, we know flux density B equal to mu naught mu R into H. So that would be mu naught mu R N into I divided by Lm. Right? Now if I have a flux phi, I will have an induced EMF E. So E equal to N into d phi by dt, right? And what is phi? Phi is the flux, B is the flux density. So flux per unit area is B. So if I look at it, this is N into D into A into B by dt, where A is area of the coil, right? So now I can write this as N A into dB by dt. We already know dB, so I can now put N into A into mu naught into mu R. Again there is another N by Lm. These are all constants. Only thing that is a variable is the current di by dt. So now we call this as induced EMF E equal to L di by dt, where L, from here we can write mu naught mu R A N square divided by Lm. So we also call this as the self inductance. L is also called self inductance of the coil. So we will come back to L a little later. It's also possible that I have N1 and I have N2, and if I send a current I here, that generates voltage in the other coil N2, because there would be a flux generated by, right? So we call these as phi 1 2, right? So we can write now there will be an induced EMF E2 is equal to N2 d phi D12 d phi 1 2 by dt. If all the flux generated by the N1 turns of coil links with N2, then I will have the ideal transformer equation. E2 will be N2 by N1 into E1, where I apply E1. Okay. Of course, we are only looking at ideal coils. A practical coil, of course, will have winding resistance, distributed capacitance, and so on. We will look at it little later. Okay. So let us now take the simple inductance. I know, let me not, okay, L1, let it be L1. L1 is equal to mu naught mu R A N1 square by Ln. Okay, so the thing is, I can vary the area, I can vary mu r, I can vary Lm, and hence get an output. In this, A is normally not popular because changing the area is quite difficult, right? Again, changing the number of turns is also not very nice, right? On the other hand, Lm can be changed, okay, and we can easily use that. So if I change Lm, I can rewrite this as An1 square divided by Lm by mu naught mu r. Oh, I'll take yeah, right. What I have done, I have taken the numerator and then put it in the denominator like this. So this we put it as n1 square, where r is called the reluctance of the magnetic path. So in fact, we normally call the reluctance as equivalent to the resistance in the electrical circuit. In the magnetic circuit, reluctance behaves like a resistance. If reluctance is more, flux is less. If reluctance is less, flux will be more. For the same given magnetomotive force. Okay, so we change Lm, right? If Lm is changed, right? If Lm is varied, then reluctance varies. So when we change Lm, the transducer is popularly called variable reluctance inductive transducer. Now, of course, how do I change Lm? One possible. So I take a right. I put a coil of n turns, and I have this rather U-shaped one, and I put another piece. I hinge it. I move this by delta G. So this is the air gap G, and that air gap changes to G plus or minus delta G. Okay. So now if I send a current I here, let me change the color, I here, I know my H would be, I can straight away write the flux. Flux phi we already know is equal to mu naught mu r Ni A by L. Right? Please let's go back and see. So here I have B is equal to mu naught mu r Ni by Lm. A into B will be my flux. Right? So this again I can put it as Ni A Ni by Lm by mu naught mu r, right? So for this I have two paths. I call this as Li, the path through the ion, right? The magnetic circuit, and there is a path through air gap. Okay, so what I can now write it as phi is equal to A N I divided by L M L ion by mu naught mu r plus G plus or minus delta G by mu naught mu r. So now I can write this as uh, L. Again we have what is L? Mu naught mu r n square A by Lm. So this again I use this ideology. So I can say this is n square A by Lm by mu naught mu r. This for this particular, right? There are two reluctances, so I can write n square A divided by Li by mu naught mu r plus G plus or minus delta G by mu naught. I am assuming that the area of cross section of the ion and the area of cross section of the air gap are the same, but in practice there will be a small, right? If I have ion like this, right? This is the two pole parts of the ion. The flux lines, of course, will flow like this, and at the edge there would be fringing, right? So while this area is A ion, this area would be air, AA, and AA will be slightly more than AI because of fringing. But if I keep the gap small, I can get very small amount of fringing, and in this particular case we simply do not we simply do not take into account the fringing. We simply say fringing is negligible, right? Later, of course, we can take that non-ideality and find out. So here I can take the mu naught. So I have inductance L. L is equal to, I will take the mu naught up, mu naught n square A is in the denominator. Here this is Li by mu r plus G plus or minus delta G, right? Okay, so if air gap increases, right, denominator increases, so I will have I'll put this here, delta L will decrease, right? If air gap decreases, denominator decreases, so overall value will increases, so I will get minus or plus delta L, right? So this I can take it as, if I take this as K, this will be K into 1 by L by mu r plus G plus or minus delta G. Okay. So now I can take this as L minus or plus delta L equal to K into 1 by L by mu r plus G into 1, this I am taking it out, plus or minus delta G, right, by G. If I assume that delta G by G into 1 by 1 plus L by G mu R is much less than 1. I can write this as delta L by L is equal to delta G by G into 1 by 1 plus L by G mu R, right? And into, of course, there will be second order terms. 1 plus delta G by G into 1 by 1 plus L by G mu R plus delta G by G whole square and so on, right? Okay, so please remember if I have plus delta L, I have minus delta G, right? So it's vice versa. If delta G is reducing, delta L will increase, and it will go. So this is I will come here. This will be into 1 by 1 plus L by G mu R whole square plus delta G by G whole cube into 1 by 1 plus L by G mu R whole cube. All powers will be there, right? So if I plot this, right, please remember, if I have increasing delta G, I am increasing the air gap. This is inductance will decrease. Delta L will be decreasing. Okay, it's highly nonlinear. Normally, this is not a very useful transducer, but nevertheless, if I make a structure like this, right, I make a structure like this, and I put a hinge, and then put another iron piece which can move this way and move this way, right? If this is going down, this will be going up. So I will have G minus or plus delta G here and G plus or minus delta G. If this is going down, this will go up. So if delta G is decreasing on the right hand side, delta G will be increasing on the left hand side. So what I do is I put a wire throughout and take the inductance. Now this inductance would be the inverse of this due to this. So let me call this as this is L1, this is L2, this is L1, this is L2, and if I combine these two, I will get a characteristic something like this. Still not be very linear, non-linear at the end. In between, it is somewhat linear. I would call it as quasi linear. So if I look at it, when I am pushing here, somebody looks like they are pulling up, or if I push here, this is being pulled up. So we call this as push-pull type variable reluctance transducer. Now if I look at it, if L1 is experiencing delta G, I would have delta L by L would be equal to minus delta G by G. Please increasing, delta G is decreasing into 1 by L by G mu R, 1 plus L by G mu R. I call this as K dash so that it's easy for me to write, into 1 plus delta G by G into K dash plus delta G by G whole square into K dash square plus dot dot dot. Now if I look at, this is for L1. At the same time I look at L2. L2 will have delta L by L. Please remember, it's going to see decreasing, increasing delta G. So I will have plus delta G by G into 1 by K dash. Please remember, K dash is 1 plus L by G mu R. I'll write it here. K dash is equal to 1 plus L by G mu R. Okay. So I can write this as, because now positive, I will have 1 minus delta G by G into K dash plus delta G by G whole square into K dash square minus delta G by G into whole cube into K dash cube. Now because I am taking L1 plus L2, I'll get 2 delta L by L. This will be delta G by G into 1 plus 2 delta G by G whole square into K dash square plus oh, I have K dash here. So we see that the even terms get cancelled. So my nonlinearity reduces. Right? So in a push-pull type variable reluctance type transducer, there is a central portion with which we can use it as a transducer. All said and done, if you take a variable reluctance type transducer, you will not get very good accuracy. You will get linearity, appreciable linearity, but with all that, the variable reluctance type transducer is still used. We will most probably tomorrow's lecture I will talk about a special type of variable reluctance type, push-pull variable reluctance type pressure sensor, right? So I mean, why is it that even though this transducer doesn't have good characteristics, but I told you they are still used. In fact, the ones that are available are really pretty expensive transducers. We will see tomorrow in tomorrow's class. The main advantage is if I look at it, what is there in the transducer? I have iron. Of course, we don't use just iron. We use either silicon steel or nowadays we use nickel iron, right? Nickel and iron, whatever it is, a magnetic material, and copper, the wire that we wind, right? And what will happen to them when it ages? Nothing. If I ensure that the iron doesn't get rusted, right? I take enough protection. I put a seal of paint on that, or as we do in our transformers, we put varnish on the iron core in the variable reluctance type transducer, and we also ensure copper wire is insulated by using coating on the copper wire, right? Uh, then there's nothing to go wrong in the transducer. So this transducer, like transformers, if you really come to the lab, I can show you transformers that are here from the beginning of this institute, which is almost 70 years. In fact, there are transformers which are more than 200 years old that are still working in Chennai, because there's nothing to go wrong in a transformer, right? We have only iron and copper, and iron and copper really do not get, I mean, if you take enough precaution, protect it, it will last for centuries, right? So this particular transducer has a very long life, right? So whenever you want long life, you need to uh, use materials that also have a long life in the transducer. So this can work for 25, 30, 50 years, whatever number of years that. The second thing is, if I make a transducer, let's say I made a transducer, right, and I apply, right, uh, disturbance to it. Let's assume that I take a hammer and hit it, right? You may say, are you crazy to take a hammer and hit it? It is possible to have situations where the transducer has to take a beating, or what we call it as a shock, right? When I make again out of iron and copper and make a variable reluctance type transducer, uh, I can ensure that the iron is quite hardened iron, right? There are several type of steels which have extremely good strength. So even if I hit the transducer with a hammer, uh, nothing will happen to the transducer. So long life and ability to withstand shock, right? Shock or even vibration, right? So it can work in really harsh uh, environments, right? Okay. Now, the moment I have uh, inductance that is variable, I will never get this. I will get only winding resistance, and this inductance varies. So I have to get an output uh, proportional to the inductance L, and I need signal conditioning circuit. We will discuss signal conditioning circuit a little later. I am uh, jumping a little bit here for obvious reasons. Uh, the another type of inductance is that I have two coils contiguously wound, right? And this is hollow coil, so this is wound here. So I put a core inside, right? And then I move the core like this. If I look at the inductance, this coil inductance, I call it as L1, and this coil inductance will be like this. When the core is at the center, I will get half. So, and if I keep moving, this will become maximum, and if I continue to move it, it will go to 0 again. If I push this inside, this inductance will become maximum, and so we see that it's possible to get a variation in the inductance, which is quite linear in this particular range, right? So small. This is again push-pull, right? Self-inductance. Sometimes we use this, but not that popular like the other variable reluctance type. But we can use this technique for getting a more or less linear variation in inductance with respect to displacement, right? But what is really popular is that I have the same two coils. Oh, I will not. Let's say I have a former. So this is my cylinder. On this cylinder, I wind. I wind coil like this, and another coil. And I wind yet another coil in comparison, right? And then I put a plunger inside. So I put a plunger inside and move the plunger in and out. So I can now put the equivalent circuit as this is my primary. Oh, I should not use this color. My primary is this. Normally this will be N1 turns, and these two are secondaries, right? And the way that I wound it, I don't know whether you noticed it. One, I wound the secondary in the clockwise direction. The other one, I wound it in the anti-clockwise direction. So this is my dot point. This would be my dot point here. This would be my dot point here. Now I connect these two. And take the output as E0. So this is E1 plus minus. This is E2 plus minus. Please remember, wherever dot is there, that side is positive. Okay. So I can now write E0 as E1 minus E2. Right. So if I have a plunger that is moving up and down, this would have M1, this would have M2, so this would be D M is a mutual inductance, so this would be I1 into this is a current I1 into M1 minus M2 of j omega, right? So if I have this exactly at the center, M1, if I look at this is X, this is M, I will have M1 increasing and M2 decreasing, right? So if I now look at the output E0, if I put the displacement, when exactly half the plunger is with the secondary coil 1 and half the plunger is with the secondary coil 2, I call that position as X is equal to 0. And if I move it up, I call it as positive. So if this is plus X, this is minus X, this is X is equal to 0, I will get a characteristic something like that, right? Because again, please remember, we are assuming ideal inductances, right? In practical inductance, this is will change. You will see what changes, and so here I will have E1 minus E2 will be positive, and here E1 minus E2 will be negative. That's all. Magnitude. This is just magnitude of E1 minus E2. Okay. So this particular type of transducer is a very special name, linear variable inductive not inductive variable differential transformer type, because if I look at it, the variation is quite linear as I move the plunger in and out, and I take the difference in voltages, so we get the differential output, and this looks like a transformer, right? So are simply called LVDT, right? The LVDT is a very popular transducer, and the applications are quite numerous, and they are commercially available. The LVDT is commercially available. This is not commercially available. This LVDT, sorry, just inductance, not commercially available. This is commercially available. Variable reluctance, push-pull type, variable reluctance type transducer is commercially available. You can buy them, buy that, and this LVDT is quite popular for both linear displacement as well as angular displacement, because whatever I talked about in the linear fashion, I can also just bend the coil to form a circle and I can get circular movement, giving me the same amount of output, right? Same type of output. Now, if I practically build an LVDT, let's say I have an LVDT, I have a plunger here, and I put my right. So this is the dot point, this is the dot point, this is the dot point, right? Like this. So normally this is N1, this will be N1 by 2, this will be N1 by 2, because remember, we have to wind on the same cylinder through which the plunger moves. Okay, and the if I make this and get the characteristics, right, I will get something like this, right? For no value of x, this is again x, so this is plus x, which means moving upwards. This is minus x, which is moving downwards, and at the middle point where x is equal to 0, I will get a small voltage, and also there will be a nonlinearity here. You can see the curvature here. So this voltage is called residual voltage of LVDT. You cannot uh, build an LVDT that does not have a residual voltage, or in other words, all LVDTs will have a residual voltage, right? What are the reasons? The reasons are, if I look at it, I give a sine wave here, I am going to get a sine wave here, I am going to get another sine wave here. Now, whatever care you take, if I look at these two sine waves, right? So this is 1, so I have put this as 1. If I look at the second, we expect that it will be exactly 90 degrees, right? Because dot points are there. But because of practical small changes in the way that we wind the coil, in the interturn and intraturn capacitances, the winding resistance, the if I look at here, that alone I expand. So the top one is giving me a sine wave. The bottom one will have a small phase shift, right? So, which means I have root 2V sine omega t, that is this, and this would be root 2V sine omega t plus phi, right? At no point I will get a 0 voltage, right? So because of this phase shift, I will get a 0 voltage. The second problem is, if I look at a BH curve of any ion, right? Doesn't matter, ion plunger, whatever it is, I have what is known as hysteresis characteristics. So even if I put a perfect sine wave flux, I am going to get a nonlinear characteristics, because the BH, this is H, this is B, has what we popularly know it as hysteresis loop. Because the hysteresis loop creates nonlinearity, nonlinearity creates higher harmonics. Once again, the two EMFs will not cancel each other at when x is equal to 0. So, but that's not a big problem. We can handle both. Okay. So, if we look at inductive type transducers, uh, there are only these type of transducers that are very popular, that are in use in the industry right now, and we will look at the signal conditioning circuits for the inductive type transducer in the next class. So I'll stop here.